So thank you all for joining for this new reading group session, ContinualAI. And thank you, Mitchell Wartzman, for joining us today and talking about your recent paper, Supermasks in Superposition. So thank you all again for joining. And Mitchell, the stage is yours.
All right, yeah, thanks so much. Thanks so much for having me come talk at the reading group. Yeah, I mean, this feels weird because right now I can't see anyone. I can just see my slides. So
Yeah, yeah.
I'll minimize after I'm done presenting. I'll minimize the slides, and then we can sort of chat about.
Absolutely.
Okay, so yeah, thanks for having me. So I'll be talking today about this recent work, Supermasks and Superpositions, from myself and some other folks. So basically, this was at least for me and for some of these people as well, so the first kind of step into the continual learning space, which is a very cool space, which I'm sure you all think and like. But one thing that I sort of want to just before we get started, one thing that we think a lot about in the paper, or at least before really starting, is sort of what is continual learning and what are some of the problems that you may face in continual learning. And this might not be the right approach, but after reading a lot of papers, this was sort of the main things that we thought about the problem. So as you all probably know, in continual learning, you have a task, and then throughout time, you might be asked to learn other tasks. Like first you learn task 1, then you learn task 2, and you learn task 3. And if you just use a traditional neural network, you're prone to this thing called catastrophic forgetting. This is sort of the main setup, but there's kind of a lot of nuances here that we thought were really interesting. Like there's a lot of different evaluation setups, and each of them are valid and interesting, and each of them have been studied thoroughly. And there's actually been a few works sort of distilling what are these. So we found it was helpful to actually add an additional, just give these things a name that was very easy to map from the name to the scenario. So to that end, we proposed sort of this, which looks a lot like these two works, with slight modifications. So basically, yeah, these are just sort of the taxonomy and mnemonic we give for all these scenarios. Each of them are valid and interesting. And so these names that we provide consist of 2 or 3 letters, where the first 2 letters are the most important, because they provide sort of the main thing about the evaluation scenario, which is whether task ID is given during train or inference. So if the first letter is G, that means that task ID is given during train. If the second letter is G, that means that task ID is given during inference. N is not given. Yeah, so let's just walk through these scenarios. So GG is sort of you can imagine this is sort of the easiest setting. This is the setting where you're given the task ID during train and inference. So the task ID would be like task 1, task 2, task 3. So GG, given the task ID during train, given the task ID during inference. So yeah, this just looks like, okay, during inference, when you see this data point, you're told, okay, this is from task 1. And then you only have to do classification, over the task 1, classes. So for example, if you're training on dogs, and then you're training on cats and then birds, here you're given a dog and you're told, okay, this is dogs, and you only have to output sort of a distribution over dogs. So that's the scenario of GG. Then there's the GN. So when you're given task ID during training, and not inference. So during inference, you're not told, okay, this is a dog. I apologize if this is, if everyone's familiar with sort of these nuances, but at least to me, this was sort of a something that
No, totally. It's something we like. I mean, if there's
yeah,
kind of a naming convention in your paper, it's nice to see them here.
Yeah. So I mean, and I don't know. So basically, okay. So yeah. So basically, this is the the given during training, not given during inference. You're given this picture, but you're not told, okay, this comes from dogs. And now there's sort of a further subtlety here, which has been in these works that we cite here. This is called multi-headed versus single-headed. You'll see why, but we think that that's actually not the right terminology, because you can actually solve the so-called multi-headed problem without having multiple heads, which is something we're going to get to. So we instead say share labels versus not share labels. So if the labels are not shared, so this is unshare case, then when you're given this picture, not only are you not told this is a picture of a dog, but you actually have to, predict over sort of all the classes for all the tasks you've seen so far. So you see here that there's some cat classes and some dog classes, and you have to say this is a Dalmatian and it's not a Siamese. So this is the unshare case, the harder case. The share case is also equally valid because, maybe let's say that one of your tasks is adult dogs and one of them is puppies, and it actually makes sense to share this label space. So that's the shared case. You just have to say pug, and pug is the same class for a puppy as it is an older dog. So one thing here is that the shared case is much easier because you think about, okay, let's say I have 10 classes per task and 100 tasks. The shared classes you're still only doing 10-way classification at the end, right? But in the unshared case, you're doing 1,000 ways. So the unshared case is a little harder. So now there's the next case, the final case, which is the NN case. So this is when you're not given task ID during training, not given during inference. And actually, the Zeno paper does a much more nuanced characterization of this. But yeah, for the of this work, we find that so what this means is that even during training, you're not actually clear when tasks are changing. So the training will be on adult dogs for maybe a couple epochs, then it will switch to puppies, and you actually don't know when this you're not told when this task shift is happening, and in our setting, you actually don't even know how many tasks total you're going to see. Yeah, so these are the scenarios, and now let's try to sort of propose a model, building off of lots of other work that's going to actually perform in these scenarios. So we're going to present sort of this model, supermasks and superposition, which we call SupSup. So it's going to be a model using task-specific components. So what we mean by this is that there's a whole bunch of different ways to solve continual learning problems. Each of them are very, very cool and interesting. Some of them use generative models, some of them use replay, some of them use regularization. But there's this newer branch of solutions which uses task-specific components. So they change the model to be different based on the task. So like you can imagine not true for continual learning, but so far it's sort of limited to the GG scenario, right? The scenario where you're given the task ID during training and inference, because you have to know, okay, how should I change my model? So what we're going to do is we're going to try to have a task-specific model, so a model without a generative model, without any sort of replay that's not limited to the GG scenario. So to do so, we're going to make use of two things. One is the expressive power of subnetworks, and the second is inference of task ID as gradient-based optimization. And so now let's dive into sort of both of these things. So the first is the sort of this, when I say expressive power of subnetworks, what I really mean is supermasks. And supermasks are something that's sort of it's inspired by the lottery ticket hypothesis, and it's really emerged over the past year as a really cool tool. At least I hope people find it cool for which enables people to do different things with neural networks and think differently about neural networks. So basically, the main idea behind masks is that usually achieve good performance training the weights, right? The lottery ticket hypothesis pushes us to say, okay, maybe it's, maybe we should actually think about subnetworks, right? The lottery ticket hypothesis, for those of you who don't know, is a work from iClear last year by Frankel and Carbon, which says that there exists, neural networks contain a subnetwork that trains the same accuracy as the full network when trained in isolation. Supermasks go one step further and say, these neural networks have a subnetwork that actually performs well at initialization. So instead of training the weights, we can just say, let's find a subnetwork. And since these things are so massively overparameterized, and there's a combinatorial number of subnetworks, we can actually find one of these which performs well. So, right, traditionally you're finding the best weights W such that your neural network FXW performs well. In Supermasks, you're keeping W fixed at initialization, and you're instead finding M. So, yeah, so this line of work was sort of started by Hadi Zhao et al. In 2019, and we had some work more recently, kind of building on this, and yeah, I'm happy to talk more about actually the details of Supermasks and their training if people are interested at the end. So okay, so now we're sort of equipped with Supermasks. Let's
Mitchell,
go forward. How
sorry
can
to
we
interrupt. Mitchell, if you want, you can
Mhm.
switch off your camera because people are saying that sometimes your audio is not well received. So if you want, you can switch off the camera to improve the connection.
Sounds good.
Cool, thanks.
Okay. Is there any things that people miss that they want me to go back and talk about?
Guys, if you have any question, I think that up to now, at least, it was fairly comprehensible. So, but if anyone else is willing to ask a question now to Mitchell, you can do it now.
Maybe this slide once again.
Sorry, I didn't hear that.
I think he asked if you can repeat these, just this slide.
Okay, sure. So basically, this slide's talking about supermasks. So wait, I can also, let me switch my Wi-Fi because there's a faster Wi-Fi I can get on.
Okay, cool.
Can everyone hear me?
Yes, I can.
Okay, great. Okay, so now let's just redo this slide. So this one was talking about the expressive power of subnetworks. And basically this is covering the idea of supermasks, which just says that, usually what you do is you'd sort of train the weights, right? The traditional thing to do is if I have a neural network, I'm going to sort of change all the weights such that the neural network now performs well. What supermasks are doing is saying that actually let's freeze the weights at their initialization. And so instead of training the weights, what we're actually going to do is find a subnetwork. So find this M. M is a binary mask here. So each element in M is a 1 or a 0. And we're going to keep W fixed and instead find M such that M element-wise product W, so that's sort of element-wise masking or finding a subnetwork performs well. So this is sort of was proposed in a few of these papers here. So does anyone have questions about supermasks? Is the audio better?
Yes, I can hear you very well without interference or.
Okay, great. Okay, so now so we're equipped with supermasks, and we can sort of get ready to solve this GG problem. So task ID given at train, given at test, and here if you look at sort of the work of Malia et al, and then think about supermask, there's kind of a natural answer here, which is we're just going to use a different supermask for each task. So for task 1, we're going to use supermask M1. For task 2, we're going to use supermask M2. So we're just going to learn a new binary mask, find a new subnetwork per task while keeping these weights W fixed at their initialization. Then, since this is scenario GG, so task ID is given at train, given at inference, I can actually just during inference say, okay, I'm going to, we're evaluating on task I. I'm just going to use supermask MI. But this does sort of have one sort of key advantage over the work of Malia et al., which is that in that work, they're doing a similar thing, but they're using our pre-trained network as the sort of backbone. So they're first training a network on ImageNet, and then they're going to sort of find different masks for different tasks. And this is actually much more expensive in terms of sort of bytes, because you actually have to store these weights W. One thing about that's really cool about supermasks is you don't have to store those weights W, because they're random. All you have to do is remember the random seed that you use to generate those weights. And then sort of directly on GPU, you can actually just spin up those weights as needed. So basically now we're going to tackle sort of we're just going to show performance on this split ImageNet data set, which is from Wen et al. In 2020. And basically the split ImageNet data set is going to say, let's partition the ImageNet data set into 100 different 10-way problems, and we're gonna learn them sequentially. So this was proposed in this paper that also proposed this method batch E, which is a very cool paper and method, and we like this data set. So here we're solving it as they are with a ResNet 50 model. So a ResNet 50 traditionally takes around 100 million bytes to store. And what we can find here is that we can get good performance even when the total number of bytes we're using is less than a single ResNet 50. And recall here we're using actually implicitly 100 ResNet 50s, right? Because we're learning a different subnetwork for each of them. So how do we get sort of such a low number of bytes here? And how do we even vary these number of bytes that we're using? We do so by changing the sparsity of the supermask. So you can think about that these supermasks are really cheap to store if they're very sparse. There's not very many ones in that bit mask. And we use sort of just like kind of an off-the-shelf library for storing sparse bit masks, just like the SciPy default CSC method. But I'm sure you could actually even get more of a speed up if you use some like cool compression techniques. So this is sort of performance in split ImageNet, and we see sort of a similar trend on split SciFar where this supermask thing allows us to do very well. And there's something else that we do here, which is kind of interesting, which is we call transfer, which is you just initialize the new supermask with a running mean of all supermasks learned so far. And that's the dotted versus the solid red line. And we find that it's very helpful, which is sort of surprising that works so well. But okay, so let's move on to actually more challenging scenarios. So the GNU scenario. Recall, this is when task ID is given at train but not test. So you don't know which task you're testing on. So we're going to first infer the task, and then we're going to use the corresponding supermask. So after step 1, if we do it correctly, we'll effectively be in the GG scenario. So the intuition here is that the correct mask should produce confident low entropy outputs. So if I train a model on dogs and then showed a picture of a pug, it will say, okay, this is a pug. I'm pretty confident about it, right? But if I showed a picture of a cat, it's likely going to have more of a uniform distribution over the classes. Now, this is not always the case because you can run into models with that are poorly calibrated. But for the tasks we consider, this intuition holds, and we can talk more about the end of how to sort of take these principles and then sort of try them in settings where you don't actually have this. But this intuition, at least for now, is that the correct mask should produce confident low entropy outputs. Like if it's trained on this task, it knows about this task. So, okay, so basically equipped with this intuition, what can we do? We can say, okay, let's just find the supermask that actually gives us the lowest entropy outputs. And here we can do something that's really nice and parallelizable instead of just trying out all the supermasks, which we kind of like don't want to do that. We want to have a more sort of parallelizable solution here. So instead, we're going to stack all the supermasks together when we have data from an unknown task. And we're actually going to sort of weight each supermask by a coefficient alpha I. And then we're going to change these alpha i's such that we're going to maximize the confidence. So minimize the entropy of our output distribution. In this very toy pictures here, we see that when we maximize this confidence, we converge to supermask 2. Let's make this process sort of concrete in one or two equations, just describing sort of the one-shot algorithm, I should say. So basically, first, what we're going to do is we're going to get the class probabilities with the superimposed model. So this corresponds to the most left picture. So here, instead of using any one of the supermasks, we're just going to use sort of a weighted superposition of all supermasks, like this corresponds to here. And then we're going to say, okay, we want to do this process, which is finding the supermask that's going to actually minimize the entropy. But one really sort of, if we're doing inference, we really want this to be as fast as possible. Let's consider just one gradient step. So consider doing gradient descent with only one gradient step. What you'd sort of come up with is something like this, which is just returning sort of the coordinate for which entropy is maximally decreasing. So for which supermask weight was sort of this gradient the smallest, or the negative gradient the maximum, the biggest. And that's how we're going to sort of infer which task this is. So yeah, let's look at sort of let's look at results for this. How well can we do? And it turns out we can do really well. We can even outperform these two recent methods, which have access to the task identity. So we're outperforming two recent methods which operate in scenario GG. But let me qualify this by saying this right here is on the permuted MNIST data set. So each new task is a new permutation of MNIST, the pixels of MNIST. So you can kind of create as many tasks as you want for free, because there's basically infinite permutations of the pixels of MNIST. And so this is actually quite, it's sort of a benchmark task in continual learning, but you can think about that you don't have this, if I show a model trained on a permutation of MNIST, the original MNIST images, you can expect that it's going to be a little confused. So that's sort of why the method prevails, or this simple one-shot method can prevail in this setting. So basically all this is showing is that we're actually doing, we can infer the task very well, even among hundreds of tasks. Here we're not only experimenting with entropy, but we're using another objective G, which we'll talk more about later. But basically, yeah, when we say H, that's with entropy. So yeah, okay, so now let's move on to even more challenging scenarios, which is the NNS scenario, where task ID is not given at train nor test. And all we're going to do for this scenario is that we're going to just use our same principles from GNU. Is we're going to, during training, attempt to infer the task ID. So, and if we're not able to actually infer the task ID, it's likely that this data does not belong to a task that's seen so far. And when we say, okay, this data doesn't belong to a task we've seen so far, what we do is we just allocate a new supermask and say, okay, now we're training a new task. So this is sort of our criterion for when we're uncertain when performing task ID, because we're using the gradient of entropy, as you saw before. So when this gradient is sort of uniform, we'd uniformly prefer to use kind of all supermasks learned so far. We should allocate a new one. Now let's look at the results here. This was sort of our biggest experiment, which was learning 2,500 permutations of MNIST on a single GPU in the NNS, GNU, and GNU scenarios. So we can see here that it works pretty well. I'd actually, this dip here is sort of interesting. I can talk about why the NNS method actually sort of accuracy goes down in a lot in the last epoch. It's just because when we sort of implemented this method, we said, okay, you're allowed to allocate as many new supermasks as you want with this sort of criterion. So whenever you're unsure, you can allocate a new supermask, but you only have 2,500 supermasks total that you're allowed to use. So what happened is that this pink line sort of allocated supermasks throughout the way when it shouldn't, and it ran out here at the end. So that's what that dip is, which I don't think we had time to really discuss in the paper. So there's actually more in the paper that we're not going to talk about today, or I mean, we can talk about in discussions now, but I do not have slides for at this present time. But I'll talk briefly about all these things. So one thing that we do is we sort of implicitly store the supermasks as attractors in a Hopfield network. So this is sort of saying like, okay, instead of actually storing each of these supermasks, which you have this sort of linear memory dependence on the number of tasks. Yes, you can make the supermasks really sparse, but you still have this linear memory dependence. So can we actually get around that? Can we look towards sublinear memory dependence as well? And that's sort of our one attempt in that direction. It doesn't work great, but it sort of works. We also proposed sort of that one-shot algorithm was very coarse in some ways, and we have an analogous binary algorithm, which is almost like binary search, that allows us to do much more fine-grained sort of distinguishing between different tasks. And with this algorithm, we're able to do distinguish between 10-degree rotations of MNIST. So each new task is a different small rotation, and you can imagine that this is sort of much harder to tell what task it is. We also were interested in like, okay, can we efficiently run just a forwards pass k times really efficiently? And turns out you can build off this great batchy method to do that. And that's something that we do in the paper as well. So that's just sort of like, okay, in one forwards pass, can I just sort of effectively run all these models? And you might not be surprised, you can by just making the batch bigger. So then, we have this other objective. We use entropy, but we also use this other objective G. What is it, and why is it good? We talk about that in the paper, and I'm also happy to talk about it now. Basically, G sort of tries to mimic the supervised loss. That's the high level intuition for G. So that's the paper, and I feel free to reach out to myself or any of the awesome co-authors for further questions if we don't get a chance to talk about everything today.
Oh, absolutely. Thank you so much, Mitchell, for your very interesting presentation and your paper, by the way, because I read it quickly and it was very nice and to read and easy to follow. Maybe I can start breaking the ice with a question. On the ImageNet experiment, how much does it take roughly to train a single mask on each task, right? Because you're essentially starting from scratch, I would say, for every mask. And I think that from the numbers that you showed us before, you spent I think roughly 1 megabytes to keep in memory each of these masks. But then there's no number with respect to the training times on that. So it was very interesting to understand how much does it take to train every single mask on that.
Yeah, that's a good question. So basically, in the or sort of for supermasks in general, basically the training time is pretty much exactly the training time for a regular neural network. So
okay.
It costs just as much to train your supermask network as it does your standard neural network. So when we do that split ImageNet experiment, we're training on every task for 90 epochs or whatever the standard is for ImageNet training. We saw that for SciFar, right? We had that one experiment which showed that, okay, you can do a little better, maybe train a little faster as well by initializing your new mask with a running mean of all masks learned so far. But in general, that's definitely not somewhere where our method excels, or we claim it excels. It's definitely not like, oh, it's going to leverage all this information from the past to solve new tasks quickly. That's definitely a shortcoming for sure. And
Yeah,
that's
in fact, the follow-up question was if you tested somehow the forward transfer, let's say, variation on ImageNet instead of just Cypher thing. Yeah, you said.
No, we didn't. The ImageNet experiments, unfortunately, are more expensive, so we only tested that on Cypher. Yeah.
It would be very nice to understand if that forward, let's say, variation can somehow also scale on more complex studies. Yeah, that's very cool. Does anyone have a question now for Mitchell?
Yeah, I would have a question. So you mentioned this assumption, right, about the right supermask being the most confident one.
Yes.
So, I mean, I've seen work that says sometimes neural networks can be overconfident but wrong. So did you also look into this, or did it just not happen in your experiments?
So totally, that's a great question. The answer is that's totally a problem. It's networks are often confident about the wrong things, and that's a huge barrier to using entropy. And in fact, this is sort of like, or we'd like to hope that this is sort of a first step towards these types of solutions, but by no means are we claiming that entropy is the right thing to do because of this problem that you've mentioned. So what we mentioned in the paper is that we'd really like this to be, or we'd really like to explore this with better metrics here. So one thing we'd like to do is, there's all these cool new fancy self-supervised objectives. Are these better than entropy? Like, probably. Also, can we use energy? Can we there's also a new paper that's saying, okay, your classifier is secretly an energy-based model. Can we access that energy to say, let's find the supermask that actually minimizes the energy? So, or can we actually just train more calibrated models is another thing. We do not have experiments in any of these spaces yet. The paper was, I've been told, way too dense already. So hopefully this is not an issue, and there's lots of room for future thought here. But yeah, totally. That I'm totally on board that that's a problem with entropy. Yeah.
Okay, cool. Yeah, thanks.
Hi, Mitchell. Thank you for the presentation. I'm wondering if you found some problem of remaining space to learn new submask subnetworks based on the number of tasks, or sort of problem of capacity.
Thanks for the question. So that's something that's great about Supermasks is that you never run out of capacity because tasks are allowed to share edges. So different like the subnetworks for different tasks are allowed to be overlapping. And in fact, they will be if you don't prevent them from being. So basically, for each new task, you're just learning a new binary mask, and you're storing that binary mask. And nowhere are you saying that this binary mask is actually going to be disjoint from the previous ones. So you don't. There's no notion of sort of running out of capacity in terms of actually weights in your network because you're allowed to reuse weights. Of course, if you're doing this, the superimposed forwards pass will get worse, and that's why you'll see a little bit of accuracy degradation when scaling up. But in terms of the simpler tasks that we tried, this was not an issue.
Okay, thank you.
Any other question, guys? Please go ahead without need to intervene every time.
Yeah, one question here. So I was wondering if you have something in mind that like can compress the number of masks into one. So since given the lottery ticket hypothesis, is it possible that a given, let's say, a learned mask can do well not only on the current task but also on all the previous ones? So just to, I mean, keeping only a single mask for each, let's say, task to be learned, but each mask encompasses all the previously learned tasks as well. I don't know if this is possible or not.
No, that's a great idea. I haven't thought about it, and I also have no idea whether that's possible. But I mean, that would obviously be awesome if that isn't, and that's a great idea to look for that.
Great. Okay, so maybe there could be some discussion also on the Slack. Or, I mean, if something has a good idea, please come up.
Yeah, I definitely have nothing off the top of my head.
I mean, I was also interested in a question on the same line. I mean, for example, how much in your knowledge, Mitchell, these masks are overfitting somehow the data they have been trained for? I mean, it's the same level of overfitting of the generalization capacity of a network that is trained on ImageNet, or they are more prone to overfitting? And because what I was thinking is that, I mean, in a natural image task like ImageNet, these masks, especially for the low-level representation, at least for what we have used in trained networks, normally trained networks, they should share a lot of knowledge for extracting these low-level features, right? So if they have the same generalization capability, we should be able to find an algorithm for finding supermasks that is somehow incremental also in nature, right? So that was a thought.
I totally agree. I think that's I like that terminology too, like incremental supermasks. I think that's totally the right direction. Because like, you know, then you could possibly learn a new task faster because you don't have to redo all this stuff. Do I have a good answer for this? I don't have a good answer for this yet, and I'm sorry. But that would be really awesome. So incremental super would be great.
Let us know if you have any ideas about these. I mean, you have a lot of experience now with Supermasks, so I think this knowledge should be from you. I mean, this improvement should come from you.
No, I mean, yeah, I'd love to say that I do. I mean, so like basically this experiment where we initialized the new task with the running mean of all tasks.
Yeah.
That was sort of our very last minute attempt to try to make something work. But you know, if we had better ideas, they'd be in the paper. And we are sort of you know, as much as we've worked with Supermasks, I think we're new to this space as well. So I mean, because it is a very new space, at least Supermasks. So I think, you know, anyone can make meaningful progress there.
Yeah. So, so you don't have inference, for example, of supermasks. So there's no paper telling us you have a supermask and you have also on that's not considered.
Hello? Hello?
Hello. Can you hear me? Mitchell, can you hear me?
Yeah, I can hear you now. I turned off my video. I lost you there for a sec. Do you mind
Okay.
repeating the
So
last?
yeah, I was just wondering if you had some maybe reference about the transfer capabilities of a supermask with respect to that trained model. That's just it. If they can
No,
achieve like the same performance on another task they have not been trained on.
Good question. I don't know of any study or an investigation there. Yeah, I mean, so having such a new space is exciting, but it's also bad, because a lot of these
Yeah.
questions, these really sort of natural questions, remain unanswered.
Sure. Thank you so much. Do we have any more questions for Mitchell?
Yeah, I do have one question. It's not exactly related to the supermask for different tasks, but if we look at it in a very abstract way, these are basically some sort of variational dropout in the main parent network, the ResNet 50. So in one of the works that Suya Ganguly did in deep information propagation, which is also published at IClear 2017, they said that there exists a critical point in the order chaos transition, which defines to be the main depth scale at which a network can be trained to converge. Post that point, if a network is trained, it will start to diverge. But they also showed universally that if the network has been induced any rate or form of dropout, then that criticality point is lost. Would that also affect Supermasks in terms of if you increase the depth of the whole network, and because these are some form of dropout, would that criticality point be also lost in this case?
That's a great question. I have no idea. Unfortunately, I'll have to do some reading on those papers that you mentioned, because they sound interesting. But unfortunately, right now, I definitely don't have an answer.
Right. The general question, to be more abstract, is have you tried using any other base network which are larger than ResNet 50?
Oh yes, we've tried ResNet 101. That was in the last paper, which we called "What's Hidden in a Randomly Weighted Neural Network." We tried ResNet 101, but that's the deepest that we've tried. So I'm not sure about like getting beyond that, and I don't know if we have the resources to examine deeper than that.
Thanks.
Yeah, sorry, I don't have a great answer, unfortunately.
Yeah, no issue.
Mitchell, we have another question on the chat from Jeremy. He's asking if how the network is initialized. I mean, random is initialized random, but do you use a particular initialization, or is just the normal initialization of your network?
Oh, great question. And we do a more thorough study of this in the last paper, which is called again, "What's Hidden in a Randomly Weighted Neural Network." In this paper, we're going to use only one initialization, and that's where you initialize. So all weights in a layer are either going to be plus some constant or minus some constant. So you calculate this constant is the standard deviation of the K-Ming distribution, and then you just say, we're just going to pick the sign, so plus or minus, pick the sign sort of randomly for each weight, and that's how we're going to initialize. So you can think about that, if we were storing the weights, they'd also be pretty cheap to store because you only have to store 1 bit per each weights. I don't know why this performs better than the K-Ming normal distribution. It does. and I don't know why. Oh.
All right. So any other question before letting Mitchell have his morning?
Yeah, maybe one last question. So thanks again for the talk. When I was reading your paper, it seems like in the last layer, you're using more output neurons than the classes in the task. What's the intuition for that?
Yes. Okay. That's a great question, and that's something that isn't in the slides right now. So I think that there's so basically just to for those who don't know, right, if you're doing MNIST and you're doing permutations of MNIST, you only really need 10 output neurons, right? However, we find it's really helpful to actually just have 100 output neurons, or sometimes even more. And in general, the more you have, the better this method performs. Like there's a huge difference. And there's sort of a lingering question, which is, why? And this is sort of the one thing which I don't think that we've actually answered fully in the paper, and it's because we actually don't 100% know. I'll give you sort of what my take is on why this is this helps. So basically, what you want to do is you want to a supermask MI was trained to minimize the supervised loss for task I, which we can call LI, right? So to effectively retrieve supermask MI, the best thing to do, let's say, would be to use this LI. Since it's during inference, right, we can't use this LI, right, because we only have access to that during training. But what we kind of want to do is we can sort of try to imitate this LI. Like we can try to ask, okay, what would LI do? And basically on the first 10 neurons, we don't know what LI would do, right? What it would do is it would pull one of them up and push the rest of them down, right? So you can kind of imagine that, okay, entropy is kind of also going to encourage the same thing. Maybe it won't pull up the right one and it won't pull down the right ones, but it's going to sort of at least be in the same direction. But you'll notice that the more neurons that we add in this layer, the more we're able to actually directly imitate LI, because we know what LI is going to do on, the rest of these neurons. It's going to push them all down. So the more output neurons we have, the more we're closely able to sort of imitate this supervised loss, LI. Does that make sense at least at a high level?
I think so, yeah.
And check out section G is our best attempt to sort of actually formalize that intuition. Section G, especially the sort of the first lemma in section G, and hopefully that should be pretty easy to follow. Yeah, I haven't heard any feedback yet on if that is easy to follow, but I would hope that at least the first part of that section is. So basically, an interesting thing is we tried to actually go and say, okay, can we prove anything about this in the sort of this simple setting where you're just trying to train a linear head on a random features, and if you try to prove anything about it and you don't have these extra neurons in the last layer, we weren't able to do it. But if you add these neurons, you actually can, which was pretty cool. At least that our attempt at some theory, which we definitely don't exactly know what we're doing, but our attempt at some theory kind of resembled at least some experimental results. Yeah, hope that answers that question as best as I can.
Thanks, Mitchell. Okay, cool. So maybe if you have another just last question, we can ask Mitchell to answer that. Otherwise, we will close the reading group now.
Sure. Also, feel free to email me if anyone has other questions that they don't want to ask here.
Yep. Okay, cool. So thank you again all for joining, and thank you, Mitchell, for this talk. I'm going to ask you to upload your slides on your preferred cloud service, and then if you can link that to me, I will update our forum thread about your talk so that the people can see the slides and watch the recording as well.
Okay, yeah, thanks so much. Thanks for having me.
Thank you, guys. See you next Friday for the next reading group session of ContinualAI. Thank you again, and see you soon. Bye.